I record every session, so I'll start that now.
All right.
Now, as far as the material that we want to go over, do you have any material that you can verbalize, or if you want to take a quick picture of it and send it to my email, you could do that?
I have a couple problems from my homework the other night.
All right.
So it says to find, the first one is find the zeros of this equation.
Okay.
And it's 1/2 x cubed minus x. And I just wasn't sure how to do that.
Okay. Well, always the first step you want to look for is a greatest common factor. Is there anything we can factor out of that expression?
An x.
Uh-huh. What's it leave behind?
1/2 x squared minus 1.
And now, can we factor this further? It might not look like it, but it's the difference of perfect squares. Oh, no, it isn't. No, it isn't, actually.
Huh?
But we can still use that formula for it.
Okay. Couldn't you also pull out a 1/2 from that? Then?
Yeah, I guess you could. Sure. Let's make it 1/2, and we'll leave it x squared minus 1/2. Now, regardless, x squared minus 1/2 is not the difference of perfect squares. If this was 1/4, it would be. But regardless, you don't really need the difference of perfect squares. In other words, this is going to be equal to the square root of that minus the square root of that times the square root of that plus the square root of that. So it's going to be x minus square root of 1/2 times x plus square root of 1/2.
Okay.
And that would be the answer. Now, square root of 1/2 is 1 over square root of 2. And there's something wrong with this as an answer. What is it?
You can't have a square root on the bottom.
Right, you can't have an irrational denominator. So what do I do to that 1 over square root of 2 in order to, it's called rationalizing it.
Would you just square both of them?
Well, I can't do that, but I can multiply any fraction by the number 1. And square root of 2 over square root of 2 is the number 1, so this ends up being square root of 2 over 2. And that's a much better answer. So our factors end up being 1/2 x times x minus square root of 2 over 2 times x plus square root of 2 over 2. And if we're finding the zeros, then we're going to let that equal to 0. In other words, the zeros for a function occur when y is equal to 0.
Okay.
So what are my zeros here?
They're going to be 0, positive root 2 over 2, and negative root 2 over 2.
Good. All right.
Okay. And then my next one was also find the zeros of this equation, and it's 4x cubed minus 24x squared minus x minus 6.
All right. First of all, let's talk about finding the zeros of cubics, because this is a cubic. Finding the zeros of quadratics is easy. You can either factor it or use the quadratic formula. one of the two will always find the zeros of that quadratic. The moment you talk about cubics or quartics, finding the zeros becomes about 5 times more difficult. There is no such thing as a cubic formula like there is a quadratic formula.
Yeah.
So there's all kinds of methods that can be used to find the zeros of a cubic. And every now and then a cubic might fit what's called, you can do grouping. Okay, and this problem is one of them. In other words, we can solve this by doing grouping. Not very many cubics can you use grouping to solve, but this happens to be one of them. And what I look for to do grouping is the ratio of these coefficients is the same as the ratio of those coefficients.
Okay.
So I'm going to group. Notice I have to change that to x plus 6. Now, when I look at this part of the equation, what's my greatest common factor that I can take out of there?
4.
4x squared.
Oh, yeah.
Did you give me did I write the problem down right?
Yeah.
Well, let's take out a minus 4x squared. No, that doesn't work either.
I'll check in my book.
It seems like the signs are off here, and they shouldn't be. I don't imagine they're going to give you this problem in this format.
Okay. Oh, it was plus 6.
Okay, that makes a lot more sense. That means that this term actually becomes minus 6. Notice that if I'm subtracting the quantity x minus 6, it's equal to this x plus 6.
Yeah.
Okay? And that makes a difference because now you're not used to factoring like this, but you can still do it. In other words, what you're used to doing is factoring out a monomial term. In this case, we're going to factor out this binomial term.
Okay.
X minus 6 is the greatest common factor out of this expression. What's left over?
4x squared minus 1.
And can that be factored further?
Yeah. 2x plus 1, 2x minus 1.
And your zeros are
6, negative 1/2, and positive 1/2.
Okay. Notice that had that been a negative 6 instead of a positive 6, this method would not have worked.
Yeah.
In other words, the only reason it works is because I have this common binomial, x minus 6, and I can factor it out. Otherwise, I can't do it. And if I can't do it, this becomes a problem that becomes like a 20-minute problem instead of a 5-minute problem. That's how hard it is to factor cubics normally, if they don't fit this specific method of grouping. Do you have another one?
Okay. Yeah, this one's a graphing one.
Okay.
It's f of x equals 2 minus the square root of x plus 4.
Okay? And you're supposed to graph this?
Yeah.
All right. This is a translation of an elementary function. What's the elementary function?
Y equals root x.
Uh-huh. And what does y equal root x look like? Basically that, with a closed dot right there.
Mm-hmm.
And what kind of translation are we doing here? There's actually three things we're doing. The plus 4 has significance, the minus sign in front of the root has significance, and the 2 has significance. So let's talk about the easiest thing first. What does this 4 do? Plus 4.
Doesn't it shifts the graph to the left 4?
Yes. Okay, so if this is minus 4, and I wanted to plot y equals square root of x plus 4 all by itself, it would look like that.
Okay.
What does the minus sign in front of it do?
Does it translate it over the x-axis?
It does. So now that is y equals minus square root of x plus 4. And finally, what does the 2 do?
It stretches it.
Actually, it's a vertical shift. It moves it up 2. It doesn't stretch it or shrink it. In other words, it doesn't change the shape of the curve. If the 2 was in front like that, that would be a vertical stretch. But if the 2 is being added or subtracted, and in this case it's being added, then it merely moves everything up by 2. So we take this point and move it up to there, and that's going to be our curve. So let's erase all the others. Now, just as one last check, let's make sure that that curve fits this formula.
Okay. So would you just like put 1 point on it?
Yeah.
Into that formula?
Something's wrong already with it. Because when x is minus 4, y should be 2. Oh, it is. Yeah, it starts right there. So this point, which is minus 4, 2, is on that curve.
Okay.
Now, when you're translating functions, elementary functions, the only thing to really keep in mind is do your reflections before you do anything else.
Okay.
In this case, I actually did this horizontal translation first, and then I did my reflection. Well, I should have done it the other way around. It doesn't really matter as long as the reflection is about the x-axis. And the horizontal translation, it doesn't matter which of those you do first, but it definitely makes a difference whether you add to before or after reflecting.
Okay, so as long as like the shift and the reflection are on the same axis.
Yeah. The safest way to do it is just always do your reflection first, and then you won't have to worry about it.
Okay.
If you have two different reflections, I think do both of them first, and I don't think you'll have to worry about it. Just do the reflection before you do. The key part is to do the reflection about the x-axis before you do the vertical shift, or the reflection about the y-axis before you do the horizontal shift. And the easiest way to remember that is just always do your reflection first, and you can't go wrong.
Mm-hmm. Okay. I got confused with this one. I don't know what it means. It says evaluate the function for the indicated values, and it's an equation f of x equals a double
Double radical?
There's like two lines next to each other, and then x plus 3 in it, and then two lines after that. Yeah, but the lines are doubled up.
And that's all you have?
Yeah.
Is there any legs on these lines like that?
Yeah, they go inward. Yeah, like that.
Is this the greatest integer function or the greatest, the opposite of that? There's the greatest integer function and there's the floor function.
I think it's the greatest integer.
Okay. Greatest integer function is usually, is usually designated by this. Whoops, keep writing that wrong. I don't deal with this very often. In other words, what is the greatest integer of 3.5?
I don't know what you're asking.
It's 3. It's the greatest integer. The greatest integer not greater than 3.5 is 3.
Okay.
The greatest integer of 5.1 is 5.
So you just round down?
Yeah, as long as it's positive numbers, you round down. If it's negative numbers, it's a little different. Let's graph the greatest integer function. The thing that I always know is that it's a step function.
Oh yeah, we did this a couple days ago.
And then to the negative side, it continues being the step function. But notice that that kind of gives you different answers when you do greatest integer function. In other words, if I took the greatest integer function of 1/2, it would be 0.
Mm-hmm.
If I took the greatest integer function of 1.5, it would be 1.
Yeah.
If I took the greatest integer function of -1/2, in other words, if I do this,
It would be -2, wouldn't it be?
it would be -1.
Yeah, that's right.
In other words, it's always the integer to the left on the number line. So one way you can look at the greatest integer function, if we have a number line, is it's always to the left. In other words, if I have -1⅓, that's the greatest integer. It's the integer to the left of that number. If I'm up here at 1 3/4, the number to the left of it is 1. So the greatest integer function of 1 3/4 is 1, but the greatest integer function of -1 3/4 is -2.
Okay.
Okay? And that is reflected by that curve right there. Now, there's two kind of functions. One is the greatest integer function, and the other is the least floor function. They're kind of the opposite of one another. The least floor looks like this.
Okay.
And that is the opposite. Gosh, I would actually have to look this one up to be certain of it, but I believe the least floor of 2.5 must be 3. In other words, I got to think it's the other way. I don't know. I don't deal with least floor very often. I deal with greatest integer function pretty frequently. It's definitely one that gets taught a lot in algebra. So what did they want to know about this? If f of x is equal to x plus 3, greatest integer function of x plus 3.
They just gave me a bunch of values, like a, b, c, and d. A was -2. B was 1/2.
So they want to do f of minus 2.
Yeah.
Okay? So whenever you have a function defined as f of x, and they say f of whatever's in the parentheses, then all we do is we plug in this for x. So this would be the least integer function of 1.
That would just be 1.
And that's equal to 1. Okay, what's the next one they wanted?
1/2.
Excuse me. We got to plug it into that. So f, your first one was what? F of 1?
Yeah.
So f of 1 was actually, if we plug x for 1, we get 4.
Yeah.
F of 1/2 is going to be 3.5. And what is that?
3.
Okay, and what's another one?
F of 4.2.
What's that going to be?
7.2, so 7.
Okay.
And the last one is f of -21.6.
The negatives are the only hard ones. And the only thing to remember is to round it up. So that's -22. Well, first of all, we got to plug in -21.6. So we have this -18.6. And that's -19. -19.
Okay.
In other words, go to your integer that's the immediate integer on your left on the number line. And I'm sure the other function, the floor function, is the opposite. You go to the integer on your right.
Yeah. All right. I think that's all the questions I have.
What other kind of stuff are you doing? Sounds like you're getting into factoring polynomials that are bigger than quadratics.
Yeah, today we just started on stretching and shifting graphs.
Okay, translations of graphs, transformations of elementary functions.
Yeah.
Okay, how would I graph this? The elementary function looks like this.
Okay.
So what's the consequences of that negative sign?
Wouldn't it just flip it over the x?
The y-axis.
Y.
In other words, if I'm going to do f of minus x, that is flipping over the y-axis. And if my function was originally said e to the x, and I said, what is f of minus x, it would be e to the minus x. And that's going to look like that.
Okay.
Okay? So there's only 6 things you can do to a function. You can flip it over the x-axis. The way I do that is I take minus f of x. In other words, if f of x equals square root of x, which would be this, and f of minus x would be flipped about the y-axis. So that would look like this.
Mm-hmm.
Where if I put the negative inside the radical sign. But if I wanted minus f of x, this minus in front of the f of x means that it's going to be minus square root x, and that is flipped over the x-axis. So this one here is y equals minus square root of x, and this one here is y equals square root of minus x.
Okay.
Okay? So as far as your reflections, that's all that matters, is whether it's minus f of x or f of minus x. It's kind of like the difference between even and odd functions. You've studied that?
Studied what?
Even and odd functions.
I don't think so.
Okay? Let's talk about that for a moment, because you'll get to it if you haven't yet. If f of minus x is equal to f of x, a function is even, and it means it's reflected about y. If f of minus x is equal to minus f of x, it means it's an odd function, and it's reflected not about x, but about the origin.
Okay.
Examples would be y equal x squared. Notice that the exponent is even, and this is an even function. In other words, I can't tell the difference between y equal x squared and y equal minus x squared. They look the same.
Okay.
They're both equal to x squared.
What if it
In other words, this is f of minus x, which is equal to the same thing that f of x is.
Mm-hmm.
And if that's the case, it's an even function and it's symmetrical about the y-axis. On the other hand, if I took the function y equal x cubed, now f of minus x is not equal to x cubed, it's equal to minus x cubed. So f of minus x is equal to minus f of x. That makes it odd, and it is symmetrical about the origin.
Mm-hmm.
Notice that symmetry about the origin means that if I flipped it about the x-axis and then flipped it again about the y-axis, I would have it. In other words, if I took this, flipped it about the y-axis, flipped it about the x-axis, I would have this part here.
Mm-hmm.
So that's symmetry about the origin, makes it odd, and it fits this definition. So it's related to translations and transformations in the sense that if I say have a function f of x equals x squared,
Mm-hmm.
and I want to know what this would look like, the minus sign is inside the thing, so I know that that is going to be a reflection about the y-axis.
Uh-huh.
It's the same thing.
Yeah.
Okay.
There was something I was confused on.
Okay.
With like a graph. And there's the relative max, relative minimum, absolute max, and absolute minimum. I was confused on the difference between relative and absolute.
Okay. What's the absolute minimum on this function?
Is there not one because it goes down to infinity?
Negative infinity.
Okay.
In other words, that's the lowest minimum that this curve gets to, is negative infinity. The relative, or the absolute maximum, is positive infinity. But in this section right here, we have a relative maximum and a relative minimum. And that merely means that if I have a relative maximum, it means that there is a point to the left and a point to the right that is less than this point. And if I have a relative minimum, it means there is a point to the left and a point to the right that is higher than this point.
Oh, okay.
Okay? So if I were to draw this curve, you got a lot of relative maximums and a lot of relative minimums. Here's my relative maximums. Here's my relative minimums. But none of them are absolute. Actually, this one might be an absolute max the way I've drawn it, because it looks like the absolute minimum is negative infinity, and this represents the highest point on the function, no matter from negative infinity to positive infinity. That would be an absolute maximum, but each of these would be relative maximums, merely because they have points to the left and to the right that are smaller.
Okay.
The real reason they're asking you this is because when you get to calculus, you can determine relative maximums and minimums by finding where the slope is 0. Notice that the slope of the tangent line is 0 right there. The slope of the tangent line is 0 right there. So if we have a way of figuring out the slope of the tangent line, and we do, it's called first derivative, we can determine relative mins and relative maxes by letting the first derivative equal to 0. First derivative is the slope of the tangent line in calculus. That's what it is. If I took the tangent line right here, that would be the slope of it. Certainly not 0, so that is not a relative minimum or maximum. But if I looked at this point here and took the tangent line, that slope is absolutely 0. So that's why they're talking about relative mins and relative maxes, is because it's very critical for calculus.
Okay. And what about a greatest integer function graph? Are there relative minimums and maximums for that?
Yeah. And if you ever want a real-life example as to a greatest integer function, think of age versus class you're in school. In other words, when you're from age 6 to 7 on September 1st, you go into the first grade. If you're age 7 to 8, you go into the second grade. And it doesn't matter whether you're 6 1/2 or 6 3/4 or 1 day over 6. You still go into the first grade.
Oh, okay.
Okay, so that's kind of a real-life process that fits the greatest integer function, is the grade you're in school.
Okay.
And notice that this is open loop there, closed loop there. In other words, the greatest integer function of 6 is 6.
Yeah.
Greatest integer function of 5.999 is 5. What else have you been working on?
We just started all that today.
Sorry about my last Thursday night. I know after we met, I went home and I looked on my calendar and I realized that my Thursday was full. And I had told you that Thursday was open, but I never know for sure because people can always schedule a session when I'm not here, you know.
Mhm. Yeah, it worked out fine.
Okay.
We've been doing difference quotients.
Okay.
I think we had a quiz on that, and I got that problem wrong. So,
Give me an example of a problem.
let's see. I'll try to find it in my book.
Difference quotient. You're not into calculus yet, are you? Are you into limits?
I think we've touched on limits, like limits on of an equation.
Oh, limits is what separates calculus from all of the math prior. In other words, if I said, what is the limit of x plus 3 as x approaches 2, that would be 5.
No, we haven't done that.
Okay. When you said the difference quotient, I wasn't sure. That's called the limit quotient. I'm not quite sure exactly what you mean by the difference quotient.
Okay. It says find the difference quotient and simplify your answer.
Okay.
And it's f of x equals 5x minus x squared. And then there's a separate equation that is f times 5 plus h in parentheses.
Okay.
And then
They want to know what this is, right?
Well, yeah, but there's also right next to it, it's minus f times 5
Okay.
over h.
What you're talking about is the definition of a derivative.
Mm-hmm.
Let me spell it out. First derivative equals slope of the tangent line and it's technically, mathematically defined as the limit of f of x plus h minus f of x all divided by h as h goes to 0. Does that look familiar?
Yeah.
Okay, so if our function is that, what is this limit quotient? Well, if f of x is equal to 5x minus x squared, then let's plug that in. So we want to know the limit of f of x plus h. So what is, first of all, what is f of x plus h equal to? Anything that's inside the parentheses, we plug into x.
So it would be 5 times x plus h minus x plus h squared.
Uh-huh.
Minus x plus h squared.
So that's f of x plus h. And this limit is this minus f of x. So 5x plus 5h minus x squared plus 2xh plus h squared. The algebra gets pretty sick here. Minus 5x minus x squared all over h. Did you see how I did that?
Where did the minus 5x minus x squared come from?
Because the limit is this. It's f of x plus h minus f of x. So f of x plus h was 5x plus h minus x plus h squared. That was f of x plus h.
Mm-hmm.
We still have to subtract from that f of x.
Okay.
So this was f of x plus h, and I'm subtracting from that f of x. And using parentheses here, you can't overuse parentheses. You can only make mistakes by underusing them.
Mm-hmm.
And it's definitely necessary to use parentheses on this last part. Now, what happens when you apply this limit quotient to determine first derivative is that you'll notice all of the terms without h disappear.
Mm-hmm.
Remember, I'm going to take this as h goes to 0. So once I reduce this, notice that I have a minus x squared, and I'm going to have a plus x squared. So those cancel. I have a 5x minus 5x. Those cancel. What I'm left with in the numerator is 5h minus 2xh minus h squared. That's it, all over h. And I want the limit of this thing as h goes to 0. Well, limits are difficult if the denominator is 0. But notice that in this case, I can factor out an h from the top. So I have 5 minus 2x minus h. Still have the h in the bottom, but now that cancels with that. And my answer is 5 minus 2x minus h. And I want the limit of that as h goes to 0. Well, that's equal to 5 minus 2x. And that happens to be the first derivative of that function.
All right.
And that is the toughest way you will ever have to solve for first derivative. I don't particularly like the way calculus does this because there's a bunch of very simple rules for solving for first derivative. There's power rule, product rule, quotient rule, chain rule that makes all of these easy to do. And the only tough way to have to do them is this way, is when you have to solve f of x plus h minus f of x all over h and take the limit of that quantity as h goes to 0. That's the difficult way to do it. Gives you the same first derivative, which I could have gotten by the power rule in about 5 seconds, but you haven't learned the power rule yet, so let's not go there.
Okay. All right. Let's see something.
Got about 10 more minutes here. Have you got something that we can... So you've had problems like this?
No.
Really?
Uh-uh.
So you haven't had limits, but you've had the limit quotient. Okay. It must just be giving you an early look at that. So you haven't really had limits.
Mm-mm.
All right. However, I guess what they're trying to get you to understand is that if f of x equals x squared minus x, then f of x plus h, we plug in x plus h wherever we see x. So that's what they're trying to get you to understand, is that if you have a function defined as f of x, and you put something other than x in the parentheses, you substitute that for x wherever you see it.
Mm-hmm.
Just like if I said, what is f of 3, you would have substituted 3. In other words, you'd have 3 squared minus 3.
Okay. Could you give me like an example of a stretching and shifting a
Sure.
y equals 1 over x graph? Because I'm not...
Let's talk about a more straightforward one, and then we'll talk about 1 over x. This is a standard parabola that we're used to looking at.
Mm-hmm.
And let's call that f of x. Well, what would 2 f of x be? That would represent a vertical stretch by a factor of 2. Well, in this case, 2f of x would be 2x squared.
Yeah.
Now, notice how I would plot this. For every value, let's say when x was 1 on the original function, this function here is y equal x squared. So when x is 1, y is 1. When x is 2, y is 4. Well, if I multiply everything by 2, then when x is 1, y is going to be 2. It would be that point there. And
Yes.
when x is 2, y is going to be up here, twice as high. So if I were to graph that, hold on one second, Griffin.
Okay.
Hello? Yeah, Nate, hi. Yes, I am right in the middle of a session, and if you give me 5 minutes, I will call you back and get you set up to do online. All right? Thank you. Bye-bye. Sorry, Griffin, I don't normally answer my phone in the middle of a session unless I think it's my next session. And
That's fine.
that was the case. So, in other words, if we do a vertical stretch, it makes our parabola skinnier.
Mm-hmm.
If I wanted to know what f of x equals 1/2 x squared is, since this number is less than 1, it makes it flatter.
Okay.
Because every point is going to be half what it would have been. So that's vertical stretch and vertical shrink. Now let's talk about it with the function you mentioned, 1 over x. This is a hyperbolic function, asymptotic with the x and y axis. So if I wanted to know what 2 times f of x was, well, that would be 2 over x. Okay? So if I want to know what 2 over x looks like, which is a vertical stretch by a factor of 2, well, I'll go up and I'll find this point here must be way up here. Must be twice as high. So there's one point I'm going to plot. If I go down here, well, that's got to be twice as high. There's another point I'm going to plot. Here's another point. So if I plotted 2 over x, it would look like that. Still asymptotic with the x and y axis, but I don't know what you would call it. Flatter, I guess?
Mm-hmm.
Instead of steeper. In other words, the other side of this is going to look like this. So this would represent a vertical stretch, not a vertical shrink. A vertical shrink would look like this.
Mm-hmm. And say if you had an equation like f of x equals 1 over x minus 1.
That is the same as f of x minus 1, right?
Mm-hmm. Yeah.
Which makes it a horizontal translation. In other words, if your shift is inside the parentheses, it makes it a horizontal translation, and what we're looking for is f of x minus h. So in this case, h is a positive 1, which means everything moves to the right by 1.
Okay.
So instead of being asymptotic, we can tell where the vertical asymptotes are going to go, right? Where's the vertical asymptotes go of 1 over x minus 1?
But they just go to the right one.
Exactly. Once we have our asymptotes on there, it's still hyperbolic in nature.
Just not with the x and y axis.
Right. It's with the vertical asymptote, which always is whatever makes that equal to 0. But the other way to look at this is that it is the same as f of x minus 1, which we're looking for x minus h. So h is positive. We shift to the right, a shift of 1 unit to the right. As opposed to this, that is a vertical shift.
So that would change the horizontal asymptote.
Yes. In other words, this takes your standard function and moves it down 1.
Okay.
All right, why don't we wrap it up there?
Okay.
And let's see, did you put in an email address when you signed up?
Yes.
Because I want to send you the link to this recording
Okay.
so that